Lesson 10, looking at rates of change. So let's take a look at this example, 10.1, falling prices. Let P be the function that gives the cost, P of T, in dollars of producing 1 watt of solar energy T years after 1977. Here's a table showing the values of P from 1977 to 1987. So we should be familiar with this example because we learned about this one in the previous lesson. And now we're going to look at the average rate of change between 1977 and 1987. So if you recall, average rate of change is really slope, which is your delta y over delta x, right? Your change in y over change in x, which is just y2 minus y1 divided by x2 minus x1. So when we have these two columns of the table, the first column is your input, right? Think of your functions. We have your input, or your x, and P of T is your output, or your y. So this shows the years since 1977, so at 0 years, you're right at 1977, where it cost $80 per watt to produce solar energy. All the way down to 1987, where it's gotten cheaper and cheaper over the years, because as technology advances, things get cheaper and cheaper. 10 years later, it costs only $4.51 per watt. So in order to answer this question, we would simply set up y2 minus y1 over x2 minus x1. In other words, this would be y2, 4.51, and this would be y1, $80, because they're your outputs. So this would be y2, y1, and x2 would be 10, because that's 1987 is 10 years after 1977, and x1 is 0. So given all that, we would set up this expression, so the answer is 3. 10.2, coffee shops. Here's a table and a graph that show the number of coffee shops worldwide that a company had in its first 10 years between 1987 and 1997. The growth in the number of stores was roughly exponential. So if we take a look, we can see in the beginning, the number of stores grew very slowly, very, very slowly. And then it must have started to, word got out that the coffee was great and the store was great and the coffee shop was great. So it started to really increase at a much greater rate. And that's why it's roughly exponential. And if we look at the table, we see basically all the ordered pairs that are represented here in the graph. So if we read number 1, find the average rate of change for each period of time, show your reasoning. Let's take a look at A from 1987 to 1990. So in 1987, what I did was I actually labeled my table so there's no confusion. From 1987 to 1990, I circled 87, I circled 1990, and I also circled the number of stores that correspond with 1987 and 1990. So again, the year would be the input, X, and the number of stores would be your output, Y. So for exercise A, I've gone ahead and actually drawn a line that connects 1987 to 1990 and labeled it with A. And now I know exactly what gets Y2 and Y1 and X2 and X1. So again, I'm using the formula delta Y over delta X that we learned when we learned about slope. And we have Y2 minus Y1 over X2 minus X1, which are replaced by the values 84 minus 17 divided by 1990 minus 1987. So here's your 84 minus 17. Here's your 1990 minus 1987. So the math should be pretty simple. It's 67 divided by 3. So the average rate of change is 22.3 coffee shops per year. So you're basically saying early on, between 1987 and 1990, the coffee shops are growing at a rate of 22.3 coffee shops per year. Take a look at letter B. Here we have 1987 to 1993. So we're going to look at a larger interval, right? So now it's a span of 6 years. So we're going to use the same formula, and now I've just connected 1987 to 1993, and the 17 coffee shops we started off with is now a lot more, 272. So I know that 272 is going to be my Y2, 17 is Y1, 1993 is X2, 1987 is X1. So here's my work. 272 minus 17 divided by 1993 minus 1987. And we end up with 255 divided by 6, which is 42 and a half coffee shops per year increase. So as you can see, it's between the first 3 years and the first 6 years, we're almost doubling. That rate is almost doubling. All right. Finally, let's look at example C, where we're comparing the first 10 years. The first 10 years of growth, 1987 to 1997. And once again, I've connected on the table 1997 to 1987, and look how many coffee shops there are 10 years later. We start off with 17 and now we have 1,412. So it's a very successful business, and we can determine that we can label this as Y2, and again 17 is Y1. So we're going to set up our equation, and we have 1,412 minus 17 gives us 1,395. And between 1997 and 1987, 10 years have passed. When we divide that, we get 139.5 coffee shops per year. So make some observations about the rates of change you calculated. What do these average rates tell us about how the company was growing during this time period? Well, to sum it up, you could literally just say the number of coffee shops grew very slow in the early years, but grew much faster in later years. Okay? 10.3, revisiting the cost of solar cells. Here's a graph you saw earlier. It represents the exponential function P, which models the cost, P of T, in dollars of producing 1 watt of solar energy from 1977 to 1988, where T is the number of years since 1977. So as we look at this graph, we can see that this is the cost, right, from $0, 20, 40, 60, up to $80, and this is the number of years since 1977. So this would be 1977 at 0, and this would be 10 years later, 1987 at 10. Number 1, Claire said in the first 5 years between 1977 and 1982, the cost fell or decreased by about $12 per year. But in the second 5 years between 1983 and 1988, the cost fell only by about $2 a year. Show that Claire is correct. Okay, so I'm going to use the same formula we used before, delta y over delta x. And as you can see, we have in 1982, right? So if 0 is really 1977, then 1982 is 5 years later, and I've circled that plotted point right there. So we have about 19, it's just below 20, so it's about $19 compared with 1977, the original, the first year, and 1 watt of power cost $80. So we have 19 minus 80 divided by 5 minus 0. And yes, we're subtracting a larger number from a smaller number. We're going to end up with a negative rate of change, which is fine because the cost fell. So it is negative. You could say, so by the way, the answer is negative 12.2, which is approximately, there's a double tilde again, negative $12 per year. So between here and here, so I want you guys to think back to slope and slope triangles. So here's your rise, here's your run, here's our slope triangle. If I were to connect the dots with a straight line, then we have just calculated the slope, which is, again, your average rate of change. So negative $12 per year, you could also say, is a $12 decrease per year. Notice that 12 is now positive, $12 decrease. Let's try the next interval of time. So Claire said the second 5 years between 1983 and 1988. So here we have 1983. So this would be, right here's 1983 and here's 1988. So between here and here, we have $4 minus $14 and a difference of 11 minus 6. So once again, we're coming up with that slope triangle. Here's your rise, or your delta y, which is going downhill, so it's negative. And then here's your change in x. So we have 4 minus 14 divided by 11 minus 6, which gives us our negative $2 per year, or $2 decrease per year. So Claire is absolutely correct. Number 2, if the trend continues, will the average decrease in price be more or less than $2 per year between 1987 and 1992? Explain your reasoning. Well, because this is roughly exponential decay, as the years go further, the change or the decrease is getting smaller and smaller. And because of that, it will definitely be less than $2 per year. Okay? And I wrote out less than $2 per year decrease because as time goes on, the curve becomes flatter or more horizontal, so the average rate of change gets closer to 0. Practice problems. Number 1. My hint for you here, just like we did it in the lesson, is to calculate the average rate of change using the slope formula. Delta y over delta x, you have y2 minus y1 over x2 minus x1. And I've gone ahead and highlighted which values to use, right? I've labeled day 0 as x1, day 5 as x2, and the y value associated with day 0 is 2,000, so that's going to be y1, and y2 is 1,283. So we're talking about popular trading cards, so that should be pretty simple. Number 2, a study was conducted to analyze the effects on deer population in a particular area. Let f be an exponential function that gives the population of deer t years after the study began. So here's your general form, your general equation for exponential, right? A, which is the initial, B, which is the change factor, and T, which is your time in years. The power is the exponent, that's your time in years. And the population is increasing. If here's your equation and the population is increasing, select all statements that must be true. So remember, if the deer population is increasing, your base must be greater than 1. That's my hint for you. So based on that, select all the statements that must be true. So there's probably more than one answer. You have A, B, C, D, and E. Good luck with that one. Number 3. My hint for you here, changes in early years compare with changes in later years. So when they ask you this question down here, consider how the changes are very, very little in the early years, and then all of a sudden it exponentially grows and shoots up over here. It really grows at a much higher rate. Okay? Number 4. The function f gives the number of copies a book has sold W weeks after it was published. The equation f of w equals 500 times 2 to the w defines this function. Select all domains for which the average rate of change could be a good measure for the number of books sold. So you want to come up with, remember, these are the weeks, right? W is the week, so this is your domain, that's your input. So is it 0 to 2 weeks, 0 to 7 weeks, 5 to 7 weeks, 5 to 10 weeks, or 0 to 10 weeks? Finally, number 5. This one is a throwback to lesson 6. So this should be fairly simple. It should be review. So this shows bacteria population decreasing exponentially over time. So we have an equation, right? So there's 100 million bacteria at the start, and it is the rate of decay is 2/3. And then we have another situation that's shown graphically, and the question is, which bacterial population decays more quickly? Explain how you know. So my hint for you here is you need to figure out the decay rate by looking at the graph. Here they give it to you. It's 2/3. So in order to find the decay rate, you need to divide this term, this y value by this y value, and then this y value by this y value, and this y value by this y value. So once you find, and it should be consistent, once you find that common ratio or that factor of decay, compare it with this one and tell me which population decays more quickly. Good luck to you.